Okay, so microwave source is placed between two identical slits. As represented, slits of this and that, slit is separation. Microwave is this, so this is lambda, this is D, this is, that's nothing. This is L, calculate the frequency of the microwave radiation. Okay, so which of these, all this data do you use to figure out the frequency? That's it. Right, because V is F lambda. So F is V over lambda, and V is C. So it's 3 times 10 to the 8th meters per second divided by, what is this, 0.024 meters? Sorry. So I don't know what that comes out to be. If you get the 3, that becomes 0.008. And if I move that over, this becomes 1 8 times 10 to the 11th. 1 8 is 0.125, so 1.25 times 10 to the 10 minus 10, or 10, yeah. What's that? Oh yeah, so it'd be 2.4 centimeters, right? And 2.4 centimeters is 0.024 meters. No problem, that's fine. It's good. The more you process it, the better you remember. Okay? Then on the graph below, where the x-axis on the graph below, where the x-axis represents the distance along the screen, represents the center of the pattern, sketches the intensity of the interference pattern. So you have to use xm equals m lambda L over D, right? And then, let's see, we know lambda, we know L, we know D. So you just plug everything in, you're going to get some xm, and then you're going to do something like this. Something like that. It's like the same thing on both sides. Because I think it was a 2-slit fraction, right? Yeah. And then this distance right here has to be xm. You don't have to label every one. You just have to put it in the right thing. I don't know what this is, I just tell you. And then consider the points on the screen located at x equals 0, x equals 1, 5, and 3. Rank the intensity at those points from highest to lowest, number 1 corresponding. What does this come out to be? Lambda was 0.024 meters. L was 2 meters. 2.5. And D, this comes out to be what? 0.3 meters. Okay, that's good. All right, let me go ahead and erase this then. Because if it's 0.3 meters, then that means at 0 there should be a max, and here there should be a max. Yes? So then it should be like, and what they're looking for is that there's going to be a depression at about 0.15, like your minimum zero intensity is going to be there, and then these up here. So rank them in response, or according to highest intensity. I'm thinking we're saying 1, 2, and 3, right? Because 3 should be dark. Yeah, these are the dark bands, and these are the bright bands. And you remember how, like, as you go away from the center, they get dimmer. And then justifying the ranking, I would say obviously the center band is going to be the brightest because the light. It's so. Why would you say the brightest? You don't say because the light travels in front of us. Yeah, this is dark because it's destructive. This is the brightest because it's constructive and it's central bright. I don't know, I guess you could say in a diffraction grading, the central band is the brightest. Therefore, the second band should be dimmer. You might want to say, oh yeah, okay, you could say when the light comes through the two slits and there's diffraction occurring through those slits, that distributes the energy by the square of the distance. So the farther you go away, the dimmer the intensity. You could do that. I think if you just said that the central bright band is the brightest, then each concurrent bright band goes a little dimmer. But let's see. Let me go ahead and call up. How did I open this? What's wrong? Why doesn't this look like? There's an intensity thing. Yeah, so I guess that's all you have to say. You just say that the middle one's always the brightest. Okay, so that's easy. Oh yeah, one thing that you do want to make sure is that if you start up here and go like this one's a little bit less. Like it has to be a little bit less than that one. If you make it a lot less, if you make it a little less, I don't think they care. It just has to be obviously less. Then, suppose microwave decreased. The wavelength is decreased by a factor of 3. So this doesn't even have anything to do with physics. This is, can you do mathematic proportions, right? So if the wavelength is decreased by a factor of 3, so if lambda is divided by 3, then obviously what's going to happen to the interference band, right? If it was if xm was 0.30 meters, xm prime is going to be 0.1 meters, right? Because if you make this decrease by a third, then it's going to decrease this by a third. So now I'm like, something kind of. Questions? All right, then. Suppose the material separating two slits is removed, so there's now one slit, approximately 0.2 meters in width. The wavelength is held at that. Sketch the resulting pattern. So then, if you remember this, it's held at that, so it's like a lot, a big drop. Let's take a look at what they did. What's that? Okay, that's cool. Oh, wait, so, yeah, that's E, right? Yeah. That should make sense.
But there are dark spots at 0.1, 0.2.
Oh, they went to 0.15. Oh wait, what was D in the original part? What was this slit? 0.2.
So they use a different equation to say x mid.
Well, I mean, X min should. Interesting. Let's see if I can discuss this. We'll just use this. What I was trying to do is like, yeah, so they're saying that for the single slit interference, it's going to give you the minimum, but I was trying to look in our book where it said that, but I don't see it. I will look up something and discuss this again later. So, okay, well, it's, I'll figure out a way to explain this later. If you didn't do this and put it at the wrong distance or lengths, then you just lost 1 point. Because if you have the central brighter and you have these decreasing and even, you still get 2 out of 3. But I will discuss that later. Okay. Well, let's move on to the other ones. 4. Okay, so on the top below, we're going to draw little with forces that act on the balloon. So we have F sub B up. We have F sub G, and I guess you could argue for any of this stuff. F sub H, Fg of the helium. Then you could also say the tension. So it's kind of like the weight of the balloon, the weight of the helium, and the weight of the tension. Not the weight of the tension, of course. Those would be my guesses off the top of my head. And then calculate the point force in the balloon. So then Fb is going to equal Fg of the balloon plus Fg of the helium plus the tension. Hopefully. Give us the tension? Oh no. Oh, there's a little tiny object. Represents the balloon. Yeah, okay. That's fine. And then we know the tension, if it's staying there, just heavy enough to keep, so just heavy enough to keep the balloon from rising. We know the tension to be, the tension is going to be the Fg of the mass. Yeah.
Does it give you total mass of the balloon?
Oh, do they? Oh, including the helium. I'm sorry. Yeah, so this just becomes one. So we're given that. That's nice. Okay, so then, okay, so then we just have this, which is 0.0050 kilograms times G plus the 0.015 kilograms equals g there. So it basically just becomes 0.0, that would have been 0.02. So it's just going to become 0.2 newtons basically. Or like, whatever. Because you around, multiply by around 10. Okay. You can check. Sure. Okay, that's fine. Yeah, it's around 0.2. Like on these tests, just use 10 for gravity. Makes life a lot easier. Okay, then calculate the volume of the balloon. Okay. So we know buoyant force is equal to rho Vg, right? And then, yeah, because this is the weight of the displaced fluid, and the displaced fluid is air. So that's the density of air. Does that make sense to everyone? Sure. So then, that's annoying, but let's take a look. So we know that that's true. What else do we know? We know that we know the force statement, which was said this, which was the force of gravity on the stuff plus the tension in the string, and then the tension. So we have our original force statement, I guess. And this was force of gravity on the mass. So let's see. We're trying to find the volume of the balloon. Oh. Yeah, if we know this, right, we knew this, what was it, 0.2 newtons? And we just get that right there. So then the volume is going to be 0.2 newtons divided by density of air times gravity. Does that make sense? So I just used the basic statements, the ideas that I had before. This is the definition of buoyant force, so that just gives us what we're looking for. Ready? And then a child holds a string midway between a balloon and an object. The child gets into a car, brings the balloon. And the object in the car holds the string so neither the balloon nor the object has any surface cover needs to move forward, accelerating in a straight line. What behavior does the object exhibit when the car accelerates? So we should have said when the car accelerates, it swings towards the back of the car. Right? Because can't draw little kids on, but whatever. So the string is hanging down like this, the little mass on the bottom. And then if you accelerate the frame of reference or the external whatever, if you accelerate the world forward, the car moves forward, then inertia is going to make this want to stay. Right? Object at rest, is first law. So it's going to want to stay, but when the car moves forward, that means this is going to relatively move back. Questions? Of course, once the car gets up to speed, what happens to this? It'll go back to vertical, right? Because you can't accelerate forever. That, well, technically, I guess if you want a circle, and there was no friction, you could accelerate forever. All right, so we move on. Yeah, exactly. All right, next we're shooting this thing, this particle in here. Derive the equation V equals EV for the speed of the particle moves in a straight line through the region. So it moves in a straight line through this. We know, right, going through here, FB is going up, and because it's positive, FB is going out. Sorry, FE is going up, and FB is going down. So FB is going down, FE is going up. So then I'm just going to say FE equals FB, and then that's going to give me EQ is equal to QVB, and then those Q's cancel, so I get V, and that's the velocity there. V is equal to E over B. So that's how we do this. Check. Then some particles are emitted from the surface with greater than this ratio. Which of the following describes the initial path of one of these particles immediately after entering the region? So if you look at the two forces, FB is QVB and FE is EQ. So if they have a speed greater than E over B, what changes with a higher velocity? You see that this is the one that changes. No matter what the velocity is, FE stays the same, if they're all the same charge. Let me see, some particles. Okay, so yeah, we're assuming they're all the same charge. So then if V is greater than E over B, so if we're saying that this is the V that makes it go straight, if it's greater, FB gets greater, so what is the particle going to do? Because which one's going down? And which one's going up? Right? E is going up and B is going down, right? So if V is greater than E over B, then it should go down. Does that make sense? Question? Because what we're saying is V, when V is E over B, it's straight. If V is greater than E over B, then FB is greater than FE. If V is less than E over B, then FB is less than FE. If it's less than FE, it's going to go. That work? Okay. So, which of the following describes the initial path of this particle immediately after entering and curves towards the bottom of the page? Okay, and then I would explain my reasoning by what I showed up there. That higher, as V goes up, FB goes up. When FB is greater than FE, it goes down. All right. So, determine expression for the initial magnetic force of the particle and state its direction. Okay. Leaves radioactive source travels through the region on a straight line. So here it's going through the straight line. So once again, we're saying the velocity is E over B, or E1 over B1, I guess. Or just E, sorry. Right, that's just E. So that's our constant. So that's the velocity. And the initial magnetic force of the particle in region 2. So FE is going to equal to QVB2. Everybody cool with that? So then I just plug it in. And so I get QE1 B2 over E1. So it's going to change by the ratio of these B fields. And state its direction. So now we're into the board. So FB goes up, but top of the page. And then C, determine the changes spending the magnitude, direction, of magnetic force as the particle moves in region 2. The magnitude, well, the direction of the magnetic force is radial, right? Or centripetal, center seeking. So it's gonna want to go like that. It's gonna want to make a circle. So the magnitude should stay the same in region 2, but the direction will always be radial. First it'll be up, then it'll be up to the left, and then until what's about to leave the region. Just to double check where we are, let's take a look at this. Back the car, okay, yeah, that's awesome. There we go, did we get that right? Yeah, there you go, QVB is EQ, there you go, that's nice. Bottom of the page, that's nice. Ratio of the magnetic fields, that's nice. Constant direction changes, okay, that's cool. So everything's looking good so far. Then the path is a circle, right? So we said that the magnitude stays the same, it's constant. And this is radial, and then that's going to make it a circle. Derive an expression for the charge to mass ratio of the particle, specifically noting quantities not previously the charge to mass ratio. So I'm going to just write it there. We said FB was equal to QE over B1, B2, and then that's going to give us MV squared over R. Is everybody cool with that? Like, why did I write this?
Because you're using
Yeah, it's moving in a circle, and I have no idea what to do. I have no other idea what to do. Right? I'm like, well, there's no mass here, but I gotta have mass. Well, what's the only equation that's gonna have mass? It's gonna be this is ma, right? And then I have to ask myself, how's it accelerating? Well, that's this. And then of course remember that V is E over B1 in this region. So we have M clear speaking. I have no idea how long it takes to get this rid of this. Okay. Okay, I gotta ask. I don't know. That's not far enough to get like food money or anything. Yeah. Okay. Then let's just leave at like what? Yeah, I'd like to get there like an hour. You know, that way if there's a little fluff, a little extra traffic, we get there like a half hour before is absolute mandatory. So an hour before is fine. So we'll leave around 5? Yeah. I think 5 is fine. As long as it takes, ask the bus companies if they're supposed to know what they're doing. Yeah. Okay, cool. All right, thanks. Bye. Yep. First round of CIF tomorrow night. It's funny. We're playing against this kid at my church. He walks up to me at church yesterday and goes, "We're playing you on Tuesday." I'm like, "Who are you?" Like, I kind of know him because I met him once when I was speaking in the high school group. I'm like, "Oh yeah, you're the libero for Cerritos." Okay. Well, they're ranked 7 in our division. So if he's their starting lib, he must be okay. I don't know. Huh? Well, if we're playing number 7 in the first round, that means out of that there's 5 rounds. There's first round, second round, third round, semis, and championships. So that means that's 32, right? 2 to the 5th is 32.
Yes.
So then that means we're 25. So it's better to be not in CIF. Okay, anyways. This is E over B1 squared over R. And then this side, of course, is Q E over B1 B2. Now, obviously, you can see what I can do here, right? You just cancel one of those. That's easy. And then this B1 is over there. So then that means M over Q is going to equal B2 times B1 times R over E. I think if I've done my math correctly. So put Q down here, put B1R over there, put E up there, and I, oops, just kidding, sorry. We're supposed to come up with Q over M, not M over Q. So just flip that. Q over M becomes E over RB1 B2. At least that's how that plays out in my head. So let's take a look and see if I was correct. Q then E, B1, B2 over R, yes. Is that what, 3 problems?
Yeah.
Good grief.
The more big about my life, it's tedious. We should make a check on that.
Yeah, regular is like, you just sort of stroll through physics. You guys are like, strap a rocket on your back and then see that? See that? See that? See that? See that? Gotta remember it. See that? See? Sorry. It is the nature of the beast. Well, that's probably why no one signed up for this class next year.
The bachelor's eventually just go
Yeah. There will be no honors physics next year. It's quite sad. Everybody wants to take these. No, would more people have signed up if I called it a physics B?
yeah, probably.
So the year after, not 12, 13, or 15, 14, I'll have to change it to physics B. So make sure I go back to teaching integrated science.
You still
Yep. All right, cool.
on the future.